Right now, a silent crisis is unfolding 13 billion miles away from Earth. A lone robotic explorer is hurtling through the pitch-black, freezing void of interstellar space, running out of time, running out of power, and about to face its ultimate test. This isn't Voyager 1, the spacecraft that grabs all the headlines and gets all the glory. This is its quieter, far more fascinating twin. This is Voyager 2. And as you read this, in the summer of 2026, NASA engineers are preparing to execute a high-stakes, terrifyingly risky procedure that could either save this legendary machine or kill it instantly. They are calling this dangerous maneuver the Big Bang. It is an all-or-nothing gamble, a simultaneous reconfiguration of every single remaining power system on the spacecraft. There is no backup plan. There is no second chance. If something goes wrong across the vast 16-hour communication delay, Voyager 2 will die in total silence. But why is NASA taking such an insane risk right now? What did Voyager 2 find out there in the deep dark that changed everything we thought we knew about our universe? Stick around, because the truth about what lies at the absolute edge of our solar system is far more terrifying and complex than anyone ever expected, and it all comes down to a single secret instrument that Voyager 2 carried into the dark. To truly understand the high stakes of what is happening right now in 2026, we have to look back at how this incredible journey began. On August 20th, 1977, Voyager 2 blasted off into space, actually launching 16 days before Voyager 1. The numbering wasn't a mistake or a clerical error by NASA. It was a calculated prediction of their trajectories. Voyager 1 was put on a faster, more direct path, designed to sprint past Jupiter and Saturn before charting a rapid course straight out of the solar system. Voyager 2, on the other hand, was sent on a longer, far more grueling and scenic route. It was a grand tour of the outer solar system, a mission that required flawless cosmic geometry that only happens once every 175 years. Because of that trajectory, Voyager 2 achieved something truly unmatched. It became, and still remains, the only spacecraft in human history to visit all four of the outer gas and ice giants: Jupiter, Saturn, Uranus, and Neptune. It saw them all up close. It mapped their turbulent atmospheres, measured their immense magnetic fields, and discovered entirely new worlds among their moon systems. But this incredible cosmic tour came with a massive scientific price. That price was time. While Voyager 1 crossed the cosmic boundary known as the heliopause in August of 2012, Voyager 2 didn't reach that same boundary until November 5th, 2018. That is a massive gap of 6 years and 3 months. For more than 6 long years, Voyager 1 was out there alone in interstellar space, sending back baffling data that completely contradicted what scientists expected to find. The models were failing, the theories were crumbling, and the scientific community was left deeply confused. But there was a massive problem with the data coming from Voyager 1. A problem that almost nobody ever talks about. Voyager 1 was flying completely blind. Here is the shocking truth about Voyager 1's historic crossing. Its most important tool, the plasma science instrument, had completely broken down. It didn't fail at the edge of the solar system. It didn't fail in interstellar space. It broke down in 1980 before the spacecraft even reached Jupiter on its way out. Think about that for a moment. For 4 decades before it ever touched interstellar space, the one instrument designed to directly measure the temperature, density, and speed of plasma was totally dead. When Voyager 1 crossed into the deep dark in 2012, it couldn't actually feel the environment around it. Scientists had to guess. They had to infer what was happening using indirect data from other tools like the cosmic ray detector and the magnetometer. They were staring at a massive, decades-old blind spot. But Voyager 2 was different. Voyager 2 was carrying a fully functioning plasma science sensor, a tool that had miraculously survived the intense radiation of 4 giant planets and decades of deep space travel. When Voyager 2 finally approached that mysterious boundary in 2018, it was about to give humanity its very first direct, unclouded look at the edge of our solar system. What it discovered didn't just confirm Voyager 1's findings, it completely shattered them. And what it revealed about the true shape of our cosmic home will completely change how you view our place in the galaxy. When Voyager 2 finally made its historic crossing on November 5, 2018, the data it sent back sent shockwaves through the scientific community. In November of 2019, 5 groundbreaking papers were published simultaneously in Nature Astronomy. The data was described by researchers as nothing short of historic. The very first surprise that stunned scientists was the sheer, mind-boggling thickness of the boundary. For generations, astrophysicists believed the heliopause was a sharp, distinct line. They pictured a clean cosmic wall where the hot, fast-moving solar wind from our sun abruptly stopped, and the cold, dense interstellar plasma began. They expected this transition zone to be relatively thin, perhaps a few 100,000 kilometers wide at most, but Voyager 2 proved them entirely wrong. Instead of a sharp line, Voyager 2 detected a massive, chaotic transition zone stretching roughly 100 million miles wide. And the most shocking part? This gigantic boundary layer wasn't located on the inside of the solar system where the solar wind dominates. It was sitting on the outside. It was embedded directly within what was supposed to be pure, undisturbed interstellar space. Voyager 2's functioning plasma instrument revealed that interstellar particles were actively forcing their way inward. They were punching through the heliopause like powerful roots tearing through solid rock. Tendrils of interstellar material were stretching more than 100 million miles deep into our cosmic bubble, mixing and swirling with the solar environment in ways that absolutely no theoretical model had ever predicted. Voyager 1 had seen hints of a transition, but its view was entirely different. Before its crossing, Voyager 1 had flown through a stagnant zone inside the boundary where the outbound solar wind had slowed down to a near-complete stop, losing all its forward momentum. But when Voyager 2 approached from a completely different direction, crossing at a totally different point in space, it didn't find that same stagnant zone. It witnessed a totally different cosmic structure with entirely unique plasma characteristics. 2 twin spacecraft, crossing the exact same boundary just 6 years apart, discovered 2 completely different worlds. It proved that the edge of our solar system isn't a uniform bubble. It is a shifting, dynamic, and unpredictable frontier. This realization brought forward a massive question that senior scientists on the mission simply couldn't answer. Stamatios Krimigas, a principal investigator for the Low-Energy Charged Particle Instrument, pointed out an even deeper mystery that baffled the team. Voyager 1 crossed the boundary at 121.6 astronomical units from the Sun. Voyager 2 crossed it at 119 astronomical units. To put that in perspective, they found the edge of the solar system at almost the exact same distance. On paper, that might sound logical, but to astrophysicists, it made absolutely no sense. Voyager 1 made its crossing during a period of solar maximum, a time when the sun is wildly active, blasting out immense amounts of solar wind and energy. Voyager 2 crossed during a solar minimum, when the sun is quiet and its output is at its lowest. Every single model dictated that the heliosphere should expand and contract dramatically based on this solar cycle. It should have been a breathing cosmic bubble. Instead, the boundary barely moved at all. Krimigas stated it bluntly: "We do not understand why." When a scientist with decades of deep space data admits they don't understand something, it means we are missing something fundamental about how our sun interacts with the galaxy. But the mysteries were only getting deeper. And the next discovery regarding temperature would turn plasma physics completely upside down. The The second massive shock delivered by Voyager 2's working plasma instrument was all about temperature. In the realm of plasma physics, temperature is defined by how fast particles are moving. The plasma trapped inside our heliosphere, carried away from the sun by the solar wind, is intensely hot, filled with incredibly fast-moving particles. Scientists completely expected that when this scorching solar wind slammed into the cold, dense interstellar medium pressing in from the outside galaxy, the temperature would drop in a predictable, gradual slope. What Voyager 2 actually measured blew those expectations away. The temperature drop at the heliopause was incredibly sharp, far steeper than any simulation had shown. The spacecraft crossed from the blazing solar environment into the freezing interstellar medium in an incredibly narrow zone. But it was the density of this space that truly changed the entire picture. The plasma inside our solar system is incredibly thin and sparse. Outside, in the vast space between stars, the plasma is significantly more compressed. By combining the data from both Voyager 1 and Voyager 2, scientists finally achieved their very first stereo measurement of interstellar density. The results were undeniable. The space between the stars is far from an empty void. It is filled with a thick, heavy plasma that is more than 40 times denser than the solar wind inside our boundary. And because Voyager 2's plasma instrument was fully operational, it did something Voyager 1 could never do. It directly measured the temperature of interstellar space for the very first time. It registered a staggering 30,000 to 50,000 degrees Kelvin. While that sounds incredibly hot by human standards, in the context of cosmic plasma, it is a freezing environment compared to the tens of millions of degrees measured just inside the solar boundary. For the first time in human history, scientists had a baseline number for the temperature of the interstellar medium. The old theoretical estimates weren't just slightly off. They had been wrong by a factor of 2. But as remarkable as the temperature data was, it paled in comparison to the third major surprise. A discovery that the legendary Voyager project scientist Ed Stone called the most remarkable of all. It turned out that the absolute edge of our solar system was doing something no one thought possible. It was leaking. This brings us to a mind-bending reality that fundamentally changes how we picture our place in the Milky Way. The boundary between our sun's domain and interstellar space is not a solid wall. It is a highly porous, leaky sieve. Particles are constantly crossing this frontier in both directions. As Voyager 1 made its approach years ago, it detected tendrils of interstellar particles punching their way inward from the outside galaxy. But when Voyager 2 approached from the south, it witnessed the exact opposite phenomenon. It detected a steady trickle of low-energy solar particles actively escaping the heliosphere, leaking out into interstellar space before the spacecraft had even reached the actual boundary line. This leakage wasn't some localized glitch or a temporary anomaly. It was confirmed at 2 completely different entry points, at completely different times in the sun's cycle, and in entirely different regions of space. The conclusion was undeniable. The heliopause is a wild, bidirectional gateway. Ed Stone described it beautifully, explaining that the heliopause is less like a wall and more like a dynamic coastline, with powerful surf constantly running in both directions, crashing at the interface of 2 vast cosmic oceans. Even right now, as both probes travel further into the deep dark, 13 and 16 billion miles away from the sun, they are still traveling through a turbulent, perturbed transition zone. They have not yet reached pure, undisturbed interstellar space. They are still feeling the heavy, lingering influence of the solar system they left behind so long ago. This entire scientific revelation was only made possible because of a brilliant, forward-thinking decision made by NASA planners all the way back in the 1970s. Working with computers that possessed less computing power than a cheap modern pocket calculator, those engineers designed a 2-spacecraft mission specifically to avoid the fatal flaw of a single data point. They knew that one spacecraft could never tell you if a discovery was a unique anomaly or a universal truth. They deliberately sent them in completely different directions to build a true, three-dimensional understanding of our cosmic home. What they could never have planned for was the dramatic survival story of the instruments themselves. They couldn't predict that Voyager 1's plasma eye would go completely dark, leaving Voyager 2 as the sole savior of the mission's ultimate scientific goal. Voyager 2 turned a planned mission into an unprecedented triumph, outliving every single operational prediction. But that brings us directly to the terrifying reality of 2026. Because that legendary performance has brought Voyager 2 to the brink of absolute exhaustion, and NASA is running out of options to keep its remaining eyes open. To truly understand why the engineering team at the Jet Propulsion Laboratory is so terrified right now in the summer of 2026, you have to look at Voyager 2's current state. The spacecraft is currently operating just 3 remaining science instruments: the plasma science instrument that saved the mission's data, the magnetometer, and the plasma wave subsystem. Together, these 3 aging tools are doing something completely irreplaceable. They are providing humanity with the only real-time, in-situ measurements of interstellar space that we possess. Voyager 2 is physically moving through that alien medium at a blistering 34,000 miles per hour, tasting the galaxy and sending the answers home. But its life support system is violently shrinking. A relentless, mathematically certain clock is ticking down in the dark. The spacecraft is powered by plutonium-238, which naturally decays over time. This decay strips away roughly 4 watts of electrical power from the spacecraft every single year. At the moment of launch back in 1977, Voyager 2 had a comfortable power budget of about 470 watts, provided by its 3 radioisotope thermoelectric generators. Today, that budget has been picked clean. Voyager 2 currently has slightly more power left than Voyager 1, which is why it can still run 3 instruments while Voyager 1 was forced to shut down its low-energy charged particle instrument in April of 2026, leaving it with just 2. But Voyager 2's tiny safety margin is vanishing fast. This brings us to the desperate gamble known as the Big Bang procedure. The engineers at JPL have devised a plan that is as brilliant as it is terrifying. The Big Bang involves a massive, simultaneous swap of powered devices on board the spacecraft. They are turning off key old components and rerouting power to lower energy alternatives just to keep the spacecraft's vital heaters running so the instruments don't freeze to death. The reason they call it the Big Bang is because of its incredibly dangerous, all-at-once execution. In normal space operations, you make one tiny change, test it, verify it, and wait days before making the next. But NASA can't do that here. The Big Bang reconfigures everything simultaneously in a single, massive shock to the system. They are sending this complex web of commands across a mind-boggling distance, where a radio signal traveling at the speed of light takes more than 16 hours just to reach the spacecraft, and another 16 hours for the response to crawl back to Earth. If the spacecraft experiences a power spike or a configuration failure during those critical moments, automated fault protection systems will trigger. The onboard safety mechanisms will mistake the transition for a catastrophic failure and begin aggressively shutting down systems permanently. The engineers are doing it all at once specifically to skip through those dangerous intermediate states as fast as humanly possible. If this high-stakes gamble succeeds, it will reclaim vital headroom in the power budget, extending Voyager 2's scientific lifespan by at least another year, maybe even longer. And the stakes are doubled because if the Big Bang works on Voyager 2, NASA will attempt the exact same terrifying procedure on Voyager 1 no earlier than July of 2026, hoping to recover enough power to resurrect the instrument they were forced to turn off in April. Voyager 2 is going first into the gauntlet, acting as the ultimate test subject because it is slightly closer and has just a tiny bit more energy to spare. What is truly at stake here in keeping Voyager 2 alive for just one more year isn't just a matter of keeping an old machine running. It is about preventing a dark age in our understanding of the deep cosmos. The questions that Voyager 2 could answer over the next 12 months are vital layers of human knowledge that no other instrument in existence can touch. Take the true shape of our heliosphere, for instance. We know the boundary is leaky, and we know it doesn't shift with the solar cycle, but we still don't know what the overall structure actually looks like from the outside. Some advanced models predict that our solar system leaves a massive, comet-like tail streaming behind it as it plows through the Milky Way. Other models suggest it might be completely spherical, or even shaped like a strange cosmic lemon. Because Voyager 1 and Voyager 2 are traveling along entirely different trajectories, one pushing toward the general direction of the solar nose, and the other charting a course toward the flank, their combined data represents the only way to test these competing theories. Then there is the mystery of the interstellar magnetic field. Voyager 2's functioning magnetometer is actively mapping the magnetic lines of the galaxy in the southern hemisphere of our cosmic bubble, providing a stark and necessary contrast to Voyager 1's measurements in the north. If these instruments die, our map of the interstellar medium stops updating forever. There is no backup. There is no secret follow-on mission waiting in the wings. There is currently not a single human-made instrument within 50 billion miles of where these two legendary probes are coasting. It will take decades, perhaps generations, before humanity ever approves, funds, builds, and launches a new spacecraft to make this long journey back to the edge. When the Voyagers go silent, our eyes in the interstellar deep go completely dark. To lose Voyager 2 would be to lose a machine that has delivered an almost unbelievable list of achievements throughout its historic life. We are talking about the only spacecraft to ever lay eyes on Uranus. During its epic January 1986 flyby, it single-handedly discovered 10 entirely unknown moons and 2 new rings around the ice giant. It measured the planet's extreme, mind-boggling axial tilt of 97.77 degrees and mapped its bizarre interior composition. It discovered a chaotic magnetic field so wildly offset from the planet's rotation axis that modern models still struggle to explain how it even forms. It is also the only machine to ever visit Neptune. During its breathtaking August 1989 flyby, the grand finale of the planetary tour, it discovered 6 brand new moons, including Proteus, a world so massive it shocked scientists that Earth-based telescopes had missed it. It clocked Neptune's supersonic winds screaming through the atmosphere at a terrifying 2,400 kilometers per hour, the fastest winds ever recorded in the solar system at that time. It gave us our first close-up look at Triton, Neptune's largest moon, capturing stunning images of active nitrogen geysers shooting freezing material 8 kilometers high into a razor-thin atmosphere. It proved Triton was an alien world, a captured Kuiper Belt object dragged into Neptune's orbit by raw gravity, its frozen surface permanently scarred by intense tidal heating. And that is just the tip of the iceberg. Voyager 2 discovered a 14th moon orbiting Jupiter in 1979. It revealed an intricate, mesmerizing complexity within Saturn's rings that completely redefined planetary science. It stood as a vital witness to the wild volcanic eruptions on Io, watching the Prometheus plume blast sulfur dioxide frost 200 kilometers into space. And perhaps most importantly, Voyager 2 captured the haunting, fractured, icy surface of Europa. It showed us a world devoid of large craters, covered in strange, reddish-brown stains tracing deep cracks across shifting ice sheets. Those exact images first planted the radical idea that a vast, liquid water ocean could be hiding beneath Europa's frozen crust. A discovery that ignited decades of astrobiology and directly inspired the massive Europa Clipper mission currently operating today. All of these world-changing discoveries came from a spacecraft launched 49 years ago. A machine built from technology that predates the modern internet, personal computers, GPS, and mobile phones. It was designed to survive for just 4 years. Yet here it is, nearly half a century later, still talking to us from the interstellar void. The high-stakes tests for the Big Bang procedure are happening right now. Throughout May and June of 2026, the brilliant minds at JPL have been working tirelessly, testing every line of code, watching the fault protection systems, and calculating the exact efficiency gains of this dangerous power reconfiguration. Because of the vast distance, every single step of this diagnostic process takes over a day of communication time alone. You send a command, and you wait. You hold your breath for 16 hours just to see if the spacecraft heard you, and then you wait another 16 hours to see if it survived the instruction. The team responsible for keeping this legend alive is incredibly small. The original engineers who built and launched Voyager 2 have almost all retired or passed away. The new generation of engineers had to completely master archaic programming languages and forgotten spacecraft design philosophies from an era before their own careers even started, just to understand how to talk to these beautiful, aging machines. This deep, specialized expertise isn't something you can find in a modern aerospace engineering textbook. It is a living, breathing institutional knowledge preserved by a dedicated handful of people inside a specific building at JPL. It is a fragile human link across 13 billion miles of empty space. They are still there, still watching the faint signals, still making agonizing trade-offs between keeping an instrument running and ensuring the spacecraft's basic survival. What Voyager 2 found at the heliopause, what its surviving plasma instrument proved about our leaky, complex, and deeply connected solar system is one of the greatest scientific achievements in human history. It showed us that our cosmic home isn't isolated from the galaxy. It is in a constant, messy, dynamic relationship with the space between the stars. Right now, two small machines, powered by the slow, fading warmth of decaying plutonium sealed inside their generators half a century ago, are coasting through the eternal dark, carrying humanity's message and keeping our scientific vision alive. Voyager 1 may be the famous pioneer, but Voyager 2 is the workhorse that filled the gap, tasted the interstellar wind, and gave us the true temperature and density of the cosmic ocean. The faint signal from Voyager 2 is traveling toward Earth right now at the speed of light, carrying the ultimate fate of the Big Bang experiment. If you want to know the exact moment NASA confirms the results of this terrifying procedure and what it means for the upcoming July attempt on Voyager 1, subscribe to this channel right now and turn on all notifications. We bring you the real science, the verified data, and the raw truth from the edge of space without any hype or exaggeration. Voyager 2's journey is one of the greatest stories ever told, and we are tracking it line by line. Subscribe now, hit that bell, and stay tuned, because the final results of the Big Bang are coming, and you won't want to miss what happens next in the deep dark.